All right, this is Physics 1101, Chapter 10B lecture, and this is going to be on Pascal's principle, Archimedes' principle, and Bernoulli's principle. All named after different scientists. Archimedes was around 200 BC. Pascal was around the 1600s. Bernoulli was in the 1800s. Or 1700s, I should say. So we'll deal with these one at a time, and this will be the last part of chapter 10. So we move on here. Let's talk about first thing, and the concept is Pascal's principle is example is we can use a very small, relatively small force to lift a very heavy object, such as a car, using this concept of pressure. So when we go back to pressure, like here, the pressure here is on this container is higher than this one, because here's where the container is at the top, and this one's here, because the pressure depends only on the depth. And in this case, if they're both at the same height, then they have the pressure is the same. So PA equals PB. Now, if this is the area of A, and this is the area of B, and say A is, relatively small, so relatively small area, maybe 10 inches diameter, so that would be, say, 0.01 meters squared. And this one is a big container, right? Say 1 meter in diameter. So B has area of roughly 1 meter squared. Then using the concept of force is pressure is force over area, right? So area of A is that. Then what we have here is the pressure of A equals the pressure of B, or force of A over the area A is equal to the force of B over the area of B. And if we rearrange these expressions, then B over A equals F over A. So if this ratio is 100, then we can lift with a force of 100 times. So if we push that, so if this car weighs 1,000 kilograms, right, which is 10,000 newtons, we can lift that with a force A of 100 newtons, which is 10 kilograms, which is roughly about 22 pounds, which is not very much. I mean, you could do that by yourself. So we have a relative, so you're pressed down on a piston, you could actually lift a car. Now, granted, what's going to happen is it's going to have to move much more to account for that. So you're going to have fluid coming in, but that's how you can lift a relatively heavy object. That's how a hydraulic lifting system works. Right? So that's Pascal's principle. So keep in mind that it's using the fact that the pressure is the same, and then we have this expression from there. So that's Pascal's principle in section 10.5. Moving on here then, we're going to then, I'll leave this here for a second. If you have any questions, let me know. So moving on, we're going to go into the concepts of Archimedes' principle. All right, now Archimedes was, a lot of, engineer, scientist, a Greek philosopher, mathematician and stuff. And the question came up is, the king of wherever it was, wanted to know whether his crown was made of gold, pure gold, or had it been mixed in with some other metal, such as lead, right? Now, if you go back to gold and lead, gold has a density of 19.3 times the density of water, and lead is 11.3 times the density. So they're kind of heavy, but there's significant difference between the two. So the question was, could you find out what this was? Now what he could do, if we have a cube, a known cube, right, say 1 centimeter on each side, right, then the volume would be 1 cubic centimeter. And then if we weighed it, so weigh it with the scale like this one here, and if it turns out to have a mass of 19.3 grams, then the density would be mass over volume would be 19.3 over 1, which would be 19.3. Now, if it's made out of all lead, density of lead is that. So if it's made out of lead, then it would be 11.3. And if it's a mixture of both, say half lead, half gold, then it would be somewhere in between, which would be about maybe 15. So if he got a value of, say, 15 grams per cubic centimeter, you would know that this thing was highly contaminated with lead. And the guy that made it probably stole half the gold, and that's not good. So he had to figure out a way to find it, but you can't melt it down and turn it into a cube and do it that way. So he had to come up with an idea of how to measure this. And so he was thinking and thinking and thinking. And the story is that it was actually documented, is that he was getting into his bathtub, and he noticed as he got into the bathtub, and I'll get something here, say this jar, he got into the bathtub, he noticed that the water level went up. All right? So what he realized is that the weight of this thing was, as it falls, forces the water level to rise up, which also meant that the water was pushing on this upwards. So there's what we would call, in this concept, is this thing has a force of gravity, right, in air, and then in water, you still have force of gravity pulling down, but in water, you have a buoyant force pushing upwards. All right? Okay. And what this would mean is buoyant force is then given by the expression of rho, density of the object, divided by the density of water, which would be the buoyant force, or the force, the pulling down, would be the density, right, which would be the density so without knowing, the problem is without, what this means is that this then equals the force in air divided by the force in air minus the force in water, the weight in water, which would then be the force over the buoyant force, which is given by the weight in the air, weight in the water. So this is Fg is weight in air, Fw is weight in water, and if we subtract the two, then we end up with the buoyant force, which then depends on the mass and the volume. And what we can calculate that, so this is how we can do this. So this is the expression for the density of the, so this is 1. So the density of the object, relative, since this is 1, will be the weight in air divided by the difference of the weight in air minus the weight in the water. Okay, so let's try an example here. Right, so here's the expression. And we get this from realizing the density of water is 1. So that's how we get that. All right, so let's do an expression here. Let's do an example. So yeah, so as a result with his thing, when he realized he could do it, he jumped out of the bathtub and ran through the streets of Athens, apparently, yelling the term Eureka. Eureka discovered it, and everybody thought he was kind of crazy then. So let's take this example. So we have this brass, which has, so brass, which is roughly copper, has a density of roughly 8 grams per cubic centimeter, right? So what we're going to do is first weigh this in air, okay? And we're doing it in grams, and has a weight of 200 grams. Okay, roughly 200 grams. Okay. I'm now going to weigh this in water. Here's the original mark at 200. And now I'm going to weigh it in water. And it has, here's the 200, here's at 175. It's probably hard to see what the difference is there, but this is the weight in the water, and that turns out to be 175 grams. Now we can do it in grams, newtons, pounds, whatever. So because this is density compared to water, this is dimensionless. So then we would have 200 over 200 minus 175, which is 200 over 25, which is 8 grams per cc. So this confirms that this is actually water, brass. Now if I have something else, all right, it's going to have a density. Let's see if I can do this. This is aluminum. Container, aluminum cylinder. Wrap this up. Okay. All right, so let's just try see if we can get this to work. Let's try some tape. Probably trying to use it. That'll work. That's good enough for now. All right, so we're going to start with this. We got aluminum. All right, so this is for brass. And we'll try. So in air, it weighs 115. Okay. Now we're going to try this in water. And now it weighs 75. Okay. So the difference will be 115 over 115 minus 75, which is 115 over 40. Which is roughly 2.8. Now if you look up the density of aluminum, that is 2.7 grams per cubic centimeter. So it works. So you can see the lighter, the closer this gets to density of water, the greater the difference is going to be. So if it's an extremely heavy object or extremely dense object, like gold, the difference between in air and water is going to be relatively small. So that's Bernoulli's, that is Archimedes' principle. So that's 2 principles we've done today. And we'll finish up with the last one of Bernoulli's principle. Okay, so that's Archimedes' principle, and this is the expression that's used. Weight in air divided by the difference of weight in air minus weight in water will give us the density compared to air, compared to water. All right, last thing is Bernoulli's principle. All right, named after David Bernoulli, or Joseph Bernoulli, can I remember which one? Oh, it doesn't matter. Anyway, yeah, Daniel Bernoulli. Okay. Ooh. Lived from 1700 to 1782. And this is a concept of, if you can look at a plane wing, right? A plane wing has air flows over it, and the top part is relatively curved, the bottom part is relatively flat. So what do we have here? Well, this is the concept of what happens, right? Air flowing over a wing, and so we have air flowing below, so this speed of V, A, well, let's call this A on the bottom, B on the top, so B, A and B. And we can look at this, let's look at a little demonstration. If I have this piece of paper, all right, and I blow on it on the bottom, you would expect that the air coming out would lift this up. But you can see it has relatively little effect on lifting it up. It just kind of goes straight down. Now if I blow on top, on the other hand, you can see in that case it has a tendency to cause it to lift. Well, what's the reason for that? Well, what's happening is the air flowing on top is moving by as compared to on bottom, because when we have an object, all right, normally the pressure of air all around, so it's not moving. The pressure all around it, PB and PA is equal. If it's not moving, the pressure around it is all the same. If it is going through the air, there's a concept then that because this air is going faster, it can't have, that air isn't capable of pressing down on it. So what we have then is the concept of PA plus 1/2 rho VA squared equals PB plus 1/2 rho VB squared. Or what this basically means is that the pressure goes as the square, so the ratio of the pressure PA over PB is equal to VB's, because these will cancel out, so 1/2 rho VB squared over 1/2 rho VA squared, or VB squared over VA squared, meaning it goes as the square of the speed. All right, so this can be a very significant pressure difference. So in other words, VA, because if this is going faster, then, so if B is greater than A, because it's going faster to catch up on the other side, then PA is greater than PB, and we end up with lift, right? So this is how an airplane wing works. It flies faster, so it goes as a square of the speed, so it's quite significant. I mean, Bernoulli's equation is a little more complicated than that. It's a height difference and stuff. But basically, that's the concept of it, how a plane wing works. And I'm not going to get into the details of it too much or calculate, but that's how the whole thing works. as far as the concept. It also has, this Bernoulli's principle has a concept related to baseballs. Because it spins, the air on one side is going greater than the other, or a golf ball causes it to lift or spin or do a curveball, or causes a golf ball to farther than it would otherwise because of this effect of lift. So this is the expression, and so again, as we see here, this will be greater than PB. So in this case, the pressure, so PA is greater than PB, and the lift is given by PA minus PB as far as the pressure is concerned. And if the force, again, pressure is force over area. And so if the force is roughly, the area is roughly the same, the force lift, F lift, is basically given by that, all right? And so we calculate for how much lift. So a plane wing can lift many tons because of this principle. Now, if we also look at this, this has to be what they call laminar flow. So it can't be too tilted. I mean, you get a little bit in the bottom case here. If it's tilted too much, what you get is turbulence behind it, and that causes it to not work anymore. So if you get too much of a tilt, there's not enough, it starts turbulating back here, and you have problems there, all right? So this is also the same principle of how a car, these sleek cars, race cars, use Bernoulli's principle in reverse by having air pressure pushing down to keep it on the road. And that's the case there, as far as that's concerned. All right, one last thing here I'm going to do for chapter 10 will be the continuity equation. And this will be continuity and this is pretty straightforward, and this is the case of if we have, this has an area A 1, this is area A2 coming out, then the volume okay, so this is moving some speed V1. This is moving at some speed V2, and since the volume going in equals the volume coming out, volume rate, A1 times V1 is the rate coming in, and that has to equal the rate coming out, so the ratio of these are this. So the ratio, so basically then A1 over A2 is V2 over V1. So the greater this ratio is, this there will be the same. So if this has a ratio, if this has an area of say 1 meter squared, and this is an area 2 of 0.1 meters squared, and if V1 is coming in at 1 meter per second, then V2 will be equal to A1 over A2 times V1, which would be 10 over 0.1 times 1 would be 10 meters per second squared, 10 meters per second. So we'd come out at 10 meters per second. Because of that also, if we have a pressure gauge here, P1 and P2, right, I'm not going to get into details of that. P2 will have a smaller pressure than P1. When the water is stationary or slower, it's going to have a greater pressure than when it's coming out. And this is also due to Bernoulli's principle. So this is the continuity equation, and this is for liquids primarily, as far as that's concerned. Okay, so that is all of chapter 10, and then I will start on chapter 11 later this week, and that'll be on oscillations and dealing with the simple harmonic motion, the pendulum we'll be doing. So that'll be parts of chapter exam 4